I wanted to show you all something great. This is, my mom made this. I told her about the aperiodic tiling. She started to making a quilt out of it. I thought it was great. I just wanted to impress you all with my mom's skills. I haven't seen it in person. I don't know actually how big those things are, but thanks, Mom. All right. Let's talk about connectedness some more. Thank you for coming, by the way. Connected sets. I hope everybody remembers the idea. I mean, it's a very simple, very intuitive, basic idea, but if you have a set which is sort of in two pieces like this, then that's disconnected. And what disconnected means that there is a separation. Good morning. Disconnected means there is a separation. X equals U union V, and the U and the V are basically the two pieces, right? Although if there's more than two pieces, then it could be like maybe the U is two of the pieces and the V is one other piece or whatever. But anyway, a separation means X equals U intersect V and X equals U union V. U intersect V is empty. That is, the two sets are disjoint. Also, the two sets have to be open, and they individually cannot be the empty set. So U is not the empty set, V is not the empty set, and U and V are open. All right, that's what a separation is. It's kind of a lot of stuff here, although the idea of it, I think, is very natural and very simple. There's a lot of little details in the definition. All right, that's called a separation of X. And if such a thing exists, then X is disconnected. And if there is no possible separation, then X is connected. And we did a bunch of examples last time. Remember, what I wanted to talk about this time is this basic, well, it's not terribly basic, but the idea of a continuous function and a connected set is if f x to y is continuous and x is connected, then f of x, the image of the set or the range of the function, is also connected. This is sort of my goal for today, or I mean, this won't take the whole time. Connected. The range, if the domain is connected of a continuous function, then the range is also connected. It's not necessarily true that y, the whole space, is connected just because y. You can have x being all one piece and the range being all one piece, even if y has like extra pieces, just the function never goes there. But the range has to be all one piece. And I said last time, this is basically what the intermediate value theorem says in calculus, but this is a much more general version of that. Now, one preliminary that we need to talk about before discussing this is the conclusion here is f of x is connected. Really, I should say f of x being a subset of y is connected, right? But actually we haven't really talked about what this means exactly, because we've only talked about what it means for the entire topological space to be connected, like x is connected or y is connected. But this is a subset inside of a topological space, and we haven't really discussed that. So a slight detour with no complicated ideas, but there are some details to work out. What exactly does it mean? So in general, let's just talk about connectedness of a subset of x, right? We already know what it means for x to be connected. Basically, it means the same thing, but it means that A is connected if you consider A using the subspace topology, which is the natural thing to do here. So connectedness of a subset A, we say A subset of X is connected when A is connected as a space using the subspace topology. All right. This is a little unwieldy to think through. What exactly does it mean if I'm using like these properties up here of us defining a separation? What exactly do they look like if I'm talking about something using the subspace topology? And this is just the sort of slight details that we need to discuss. So what this means is, if you sort of look through all the definitions in terms of what it means to be open in the subspace topology or whatever. So what this means, basically the picture you should have in mind is X itself, the entire thing, maybe is connected, but I'm talking about a subset of X which is disconnected. So A maybe is in like two pieces like this. All right, let's say this is, I'll use my colors here. Let's say the blue thing is A, right? So I'm talking about a situation where maybe the entire space is connected, but there's a subset which is disconnected. What do I mean when I say A is disconnected inside of X? It means, again, it means you can separate A, although the separation uses open sets from X, so it is slightly different. The idea here is that the separation looks something like this. Here's my U, and here's my V. All right, that is a separation of A using open sets from X. This is what's a little bit different, is that the open sets, you can't really say they're open as sets of A because they are not necessarily totally contained in A, they are in X, all right? So what that means, if I were to write out the details of what this is supposed to mean, it is, first of all, that A is a subset of U union V. All right, so this is what, can I say what this means? Specifically what I'm saying, I will say this in more words. I'm gonna say U and V are a separation of A, which is a subset of X, when, all right, the first thing is A is a subset of U union V. It's not necessarily equal. When we were talking about separations of the entire space, U and V separate the space means that the entire space is the union. But here the A may not actually be equal to U intersect or U union V. All right. What about the intersection? Traditionally, we say the intersection is empty because the U and the V just make up the whole thing and they can't overlap. Actually, in this setting, it's not necessary that the intersection be empty. It's because, like in the picture here, I drew it, they actually do have some intersection. It's just that that intersection is not part of A. All right, so it's not that the intersection is empty, it's that when I do this intersection and also intersect with A, that is empty. That is to say, there's no points that are in A and also in that intersection. So the intersection might exist like it does in this picture. It's that little region there. But that little region has no points which are also in A. All right. And then the thing about the other property was U and V cannot be the empty set. That's kind of true. Really what we need to say is that the part of U, the part of A which is in U can't be the empty set, and the part of V which is in A which is in V can't be the empty set. You're not allowed to have U like over here which doesn't interact with A at all. So this needs to say A intersect U is not the empty set. I mean, I'll write it the other way around. It doesn't really matter, but U intersect A is not the empty set, and V intersect A is not the empty set. And then the last property was U and V are open. That's still, that still needs to be true. U and V are open. All right. You see a lot of U intersect A's and V intersect A's. That's because this is what you get if you translate the ordinary properties of a separation and translate them into the subspace topology. It ends up looking like this. So this is what it means for a set to have a separation. Those three properties or 4 properties, however you want to count them. Again, I think it's a natural idea, although it's just, you know, this picture is a little bit more complicated than the other one that we were talking about. But this is the way that we need to discuss when we talk about this theorem right here. That's what I want to get to. All right, any questions about that? All right, let's try to talk about that theorem then. So this is the big theorem about connected sets and continuous functions, which you could call the intermediate value theorem, although it's not usually called that, except when you're talking about it. This in the setting of calculus, we call it the intermediate value theorem. So it says if f is a continuous function, this I wrote before, but I'll write it again. And x is connected. Actually, I'm going to write it. Can I write it this way? If f is continuous, x is connected implies f of x is connected. All right, that's the deal. And when I say this over here, f of x is connected, what I mean is f of x is connected in the subspace topology, which means there is no separation in this sense right here, separation of a subspace. All right, let's see if we can do this. Now, the details are a little tricky, but the kind of, if you lay things out properly, it's more or less goes on some kind of autopilot. I would say the first big idea you have when proving this is a common theme when you're trying to prove things about connectedness. It is easier to handle disconnected than it is to handle connected, because disconnected just means that there is a separation. Here, if we assume x is connected, what that means is there is no possible separation. And that is hard to prove anything based on that, just because it's easy. It would be better if I was trying to prove something where I start with the separation and then I can use that to show something else. Using the fact that there's no possible separation is harder. So instead of doing this, we are going to prove the contrapositive, which would be the other way around, but negated each of them. Then the contrapositive says f of x is disconnected implies x is disconnected, and that's easier to handle just because disconnected is an easier concept to work with than connected. So I'm going to say, so for my proof here, we'll prove the contrapositive. This is very common when you're proving things about connectedness to prove contrapositives or prove by contradiction, because it's easiest if you can begin by assuming something has a separation. So we'll prove the contrapositive. Can someone tell me what's the contrapositive of this? Any discrete math masters? I just said it out loud, but you remember your contrapositives? Contraposition? Yeah?
Is it if f of x is disconnected, then x is disconnected?
Right. F of x is disconnected implies x is disconnected. Great. That is the contrapositive, the contraposition. All right. Disconnected, f of x is disconnected implies x is disconnected. This is a lot easier to kind of get started on the proof, because this assumption here, we assume f of x is disconnected. That means there's a separation which has those properties that I said before. So I can begin, this like gives you something to start with. Since f of x is disconnected, there exists u and v open sets with, and I will just write those properties again, u intersect v intersect a is empty, u intersect a is not empty, u intersect v intersect a is not empty, and I forgot the first one. A is a subset of u intersect v. U union V. Can I squeeze that in at the beginning? And then also, there were sort of 4 things. U and V are open, I already said that. All right, so this is what we begin with. 2 open sets that are a separation. And the picture you should have in mind is sort of there's all of Y here, and then my set, which is disconnected, is f of x. So it's sort of in 2 pieces here and here. This is f of x, and then those are inside of U and V. Maybe they look like this. They can have some overlap, but that overlap doesn't, is not part of f of big X.
So
Yeah.
is A just f of x then?
Oh yeah, I wrote A's. Sorry. Yes. A is, I meant to say f of x there. Thank you for that. Yeah, I should scribble them out and put f of x's. Yeah, sorry about that. I'm talking about, I was trying to remember that separation property so hard that I forgot that I was talking about something that was not called A. Thank you. Like so. F of x is what I'm talking about. All right, that's disconnected. There's a separation of y. We must somehow show that x is disconnected. That is to say, we will build a separation of x. That's what you have to do to show that x is disconnected. And all we have, our only tool to do that is the assumption of the theorem, which is that f is continuous, right? That's really all we have to work with. So we'll build a separation of x using continuity of f, right? Because that's all we got. So the only thing to do is to use the continuity of f. Anybody see how we could do something using the continuity of f? There's really only one place to go here. That's what I'm going to say. This is a kind of, there are a lot of proofs in elementary topology which are just kind of like, there's only one thing you could do. All the ideas are laid out before you. You just have to figure out how to patch them all together. It's like a buffet. Take what you get. You get what you get. Any ideas? I mean, first of all, could somebody remind us what continuous means in a topological sense? Someone other than this Julia? We got 2 other Julias. Somebody else too? Remember what continuous means? Yeah.
If U is open in Y, then F inverse of U is open in X.
Right. So continuous means if I have an open set in Y, then I can look at the preimage and that's open in X. Well, we do have some open sets in Y, right? The U and the V. So this is really the only thing you could ever say about something being, since F is continuous, the only thing you could say is F inverse, the preimage of U is open because U and V are open sets. Up here I said that. So since F is continuous, F inverse of U is open and F inverse of V is open. All right. Anybody want to guess what we are going to use as our separation of x? For a separation, I said we're going to build a separation of x, right? A separation of x means that x apparently is going to be in 2 separate pieces, right? Those 2 pieces each have to be open sets which are disjoint from one another. Anybody want to guess what we're going to call those 2 pieces? They are 2 open sets. Yes?
Inverse of U and F.
Yeah, it better be these 2 sets, right? That's the only way that this is going to work out. So since F is continuous, I do have 2 open sets. And so that's what we're going to use as our separation. Apparently, you know, one should be that and the other should be that. Now we have to think about, does that really work? So I will just say we'll show that f inverse u and f inverse of v is a separation of x. And hopefully this will be true based on the stuff, like we haven't really used any of this stuff yet, but that stuff is what we're going to use to show that these guys are a real separation of x, right? What does that involve? Well, first of all, so what that involves is f inverse of u and f inverse of v are open, right? That's true. I mean, we already said that. That's true because the function is continuous, right? The preimage of an open set is open. What else needs to be true? X must be the union of these two sets, right? So is that really true? X equals f inverse of u union f inverse of v, all right? Is it really true that you get everything in X by pulling back u and v? That is true because if you look at this picture up here, you will see f of x is the blue part, right? That means all the values of x go into the blue part. So if you pull back the u and the v, both of them, you will recover all the values of x, because this is where all the values of x go. They go inside of u and v. Welcome. Thank you for coming. Right? All the values from x go into this part. And so when you take the preimage of this part, you will indeed get all the values of x. So this is true since f of x is covered by u union v, right? That means any point of x actually is going to go into one of these u or v. So when I take the preimage of each of those, you actually do get all the points from x. All right? So this is another check. What else do we need? We need these two sets to have empty intersections. So f inverse of u intersect f inverse of v should be empty. This is another property of the separation. Why is that true? Well, it looks true on this picture, but we have to explain why. Why is it true that f inverse of u intersect f inverse of v is empty? That's just because u and v themselves have no points. It's because of this, right? This says there is no point where when you do the function to it, it goes in both of u and v. That's what this means. There is no point f of x where f of x is in u and it's also in v, because these three things are all empty intersection. That means that there is no point that's in both of u and v when you take the preimage. So this is really, since these things, it looks simple when I'm writing them, although you have to think it through. But this is since u intersect v intersect f of x is empty. All right, and then I believe the last thing that we need to demonstrate, so that's another check, for a separation is that those two parts, the f inverse u and the f inverse v, are both not empty. But that's because there really are some points here that go inside the u. That means when I take the preimage, there really are some points in the preimage. And same goes for over here. So I will say, finally, this is the last one, f inverse of u and f inverse of v are not empty, since there really are some points which map into u. Another way of saying that is u intersect f of a is not f of a. F of x, there is no a, is not empty. And u intersect, v intersect f of x is not empty. That's that. This completes the demonstration that this really is a separation of x. Sorry, I can't fit all of this on the page. All right. Here ends the proof of that very fancy sort of intermediate value theorem. A connected set, the image of a connected set under a continuous function is connected. It's a great thing. Any thoughts about that? We're about halfway done here. I got two more things that I want to talk about regarding connectedness today. Actually, I'm not sure if we'll get through both of them, but I would like to talk about, and maybe can we have another little brainstorming session here? I have a question for you to ponder. Actually, you can ponder it on your own or with the nearby Julia. I would like to think about connected sets and what happens when you combine connected sets together. Do you get other connected sets? So the question is, if I have, say, two connected sets, maybe C1 and C2, both connected, then is C1 union C2 connected? C1 intersect C2 connected? Or C1 the product with C2 connected? Think about these, and your answer could be yes, or no, or sometimes. If I combine connected sets together in these various ways, is the result going to also be connected? I would suggest try and just like draw some pictures for yourself. The first one, let's just say, I will say one thing about the first one. If I have two connected sets, is the union connected? The picture that I would naturally draw would be something like, okay, here's C1, that's connected. Here's C2, that's connected. Is the union connected? No. So like your immediate answer to that question is no. They're definitely not. I mean, it's disconnected because it has two parts, all right? But actually, there are some times when it is connected. So I will say no. For this answer here, no, but sometimes. Think about under what conditions will it actually be connected? Is that ever possible that they end up being connected if you take the union? You got an idea?
If they like overlap?
Yeah, if they have some intersection, then maybe they will be connected. So this will be if the conjecture is if C1 intersects C2 is not empty, then yes, right? Then they would be connected. And I think I agree. Actually, that's a theorem that we will demonstrate in a moment. It's not hard. Think about the other two. I'll give you a few minutes to think about intersections and also products. Talk to your friends if you like. Text your moms and ask them. My mom was a math major, but I'm sure she forgot the definition of connected set. Although she knows, she gets the idea, I'm sure. It's a simple idea. I'll give you a few minutes to think about it. Feeling for the second one?
Yeah, I'm not sure.
Yeah, like that particular shape would be connected. This is. See, I think if they're a little weirder, some weirder things could happen. Yes. One of those is right. It's not yes for both. it also has some separation. Any thoughts?
I'm not sure. I think it's something. This, I feel like the product is connected, but I don't know why.
Yeah, the product is. Yeah, it's not easy to say that. This one, there are some examples where it's. There's some weird shapes. Yeah. All right, can we talk about this? I see some people thinking about intersections. In my opinion, this is something, to me, I feel like this ought to be true, but actually it's not. You can make two weird shapes which are each connected, but their intersection is not connected. As I was walking around, I saw basically everybody drew, I didn't need to erase that. Basically everybody drew this picture, which are two connected sets, and their intersection is also connected. So you feel like, yeah, it's got to be true. Somebody trying to be a little bit more exotic than that drew two things that meet in one point, and that's still connected. One point still counts as connected because there's no, you can't make a separation. This point equals U intersect V, where U and V are both non-empty. That's not possible. So that still counts. And I encourage you to try to think weirder about shapes. Actually, you can make two connected shapes where the intersection is not connected, and they don't have to be all that weird. I saw somebody who shall remain nameless came up with this example. That's one shape. Can you tell where you should put the other shape now to make it so the intersection is disconnected? If you do like this, basically, but make one of the shapes look like that. Then the other shape, you know, a circle maybe. And now the intersection is here and also here, which is disconnected. Strange but true. You can take two connected things and their intersection can be disconnected. So this is like a C1 and a C2 over here. And here C1 intersects C2 is disconnected. Right? You can make it very weird if you want to, like you could do something like that and then intersected with like this, and you get many, many little guys that it's disconnected. All right? Or you could do something truly insane like remember on the homework a long time ago, you had this sort of weird infinite comb shape, and then you could take the intersection of that with this, which has infinitely many different little disconnected bits. So you can get crazy with it if you really want to. All right, so the answer to this question right here is no. And in fact, there's no real cute way to make the answer yes. Like here, this is a nice resolution to the question that sometimes it is connected. But this one actually, there's no real good thing to say about it. The intersection of two connected sets is not connected necessarily. Sometimes it is, but as far as I know, the only sort of natural thing to say about that is, like, when exactly will this be connected? The answer is kind of like when it's connected. There's not another easy way to judge when that really is going to be connected. All right, the answer to this one is yes. If you have two connected things, their product will be connected. Although that's not obvious, but the picture you should have in mind for that, for the products, is for C1 cross C2. The basic picture should be something like I have one set down here and I am taking the product with another set, and what I get is some kind of a box, right? That's C1 cross C2. Now here you can see that if C1 and C2 are connected, then the product will be this box which is also connected, although that shouldn't be an example which convinces you in general, because that's a very simple example where I'm taking two intervals, which are very simple kinds of shapes. Slightly more interesting would be, what if I have sort of a weird shape like this, and then I cross that with, say, a closed interval 0 to 1? Those are each connected. That one on the left is like a subset of R2. What that makes is something like this sort of a tall version of that. Right? It's kind of like a cylinder sort of a thing. Right? This is how I think of this product. Anyway, is that still connected? Yes, it's still in one piece, right? This should not convince you, but this is basically the kind of pictures you should have in mind. It turns out that the product of two connecteds is connected. But can we talk about the union? We got 15 minutes. I think that's enough time to discuss the union bit. So I want to actually show that as a theorem, that if you have, it's not always true that the union is connected, but this stuff, if you have this stuff additionally, then it will be true that the union is connected. So actually, the big theorem is if C1 and C2 are connected and C1 intersects C2 is not empty, right? Then C1 union C2 is connected. All right. Let's see if we can do this in our remaining 13 minutes. Like before, and this is a general theme, like I said, when you're doing stuff involving connectedness, it is a lot easier to deal with disconnectedness than connectedness. So I'm going to try to rephrase this, and your ways to do that is either you could try to prove the contrapositive, or you could just do the proof by contradiction. And in this example, it's a little nicer. The contrapositive is somewhat complicated here, so it's a little nicer to just say, I'm going to prove this by contradiction. That will give you some place to start. So I'm going to say, to get a contradiction, I assume C1 union C2 is disconnected. Discon. All right. The reason I like this a lot more is because disconnected is much easier to have as a starting point for your proof, because since I know it's disconnected, that gives me like the separation, the U and the V, and then I can say a bunch of stuff about it. Versus if you begin with this thing is connected, you don't get anything to start with. You get like a negative thing to start with. So anyway, I assume C1 union C2 is disconnected. So the picture that we have is something like C1 is here, C2 is here. They do have some intersection, right? This is the setup. And in order to get a contradiction, I am assuming C1 union C2 is disconnected. That means there's a separation of this into two pieces. Now, the way the picture looks, that's not possible, but I'm just going to imagine that it is possible somehow. So I have a U and a V. Maybe the U goes like this, and the V goes like this, and they're not supposed to have any intersection somehow. Just make them go right along the edge there, all right? I am imagining that there is a separation, C1 union C2. So that means open sets U and V with the separation properties. All right, can I just say that separate C1 union C2? You all remember those properties. All right. What are we going to do with this? This proof is less obvious how to proceed from at this point. This is the basic setup. How to proceed is you consider that intersection. Remember, we have assumed all along this intersection is not zero. And so I would like to consider that intersection. Let's just imagine we have some point. I said not zero, I mean not empty. This intersection is not empty. That means there really is a point in the intersection there. So let's take some point X in this intersection. C1 intersects C2. It's right there, right? That's my X. Now, since X is in C1 and C1 is connected, I'm going to say since C1 is connected, U and V cannot separate C1 because there is no separation of C1. All right? That means that C1, it's not possible that C1 is like partially in U and partially in V. It has to be either in the one or in the other because C1 is connected. And if it was in half and half, then that would be a separation of C1 because U and V are a separation. And so U and V cannot separate C1. So C1 is either all in U or all in V. So C1, I'll say it this way. C1 is a subset of U or C1 is a subset of V and not both. Because U and V are a separation, that U and V are disjoints, so they can't be in both. All right? And then the same goes for C2, right? Also, C2 is in U or C2 is in V, not both. All right? And we have this point X. I would like to think about all of these things are either in U or in V, but not both. What about X, the single point? X is in C1 intersect C2. Now, X being a point, it has to be either in U or in V. According to my picture, X is in U. That's the way that I drew it. But because U and V cover up this union, X has to either be in U or V. Let's just assume, for the sake of, it doesn't matter either way. I will say, without loss of generality, meaning it doesn't matter if I assume it's in the one or the other. The rest of the proof will be the same. Let's assume X is in the U, all right, as I drew it in the picture. If it's in the V, then everything works out the same way. Actually, the fact that X is in U tells you something about these things. All right, we said C1 is in U or C1 is in V. I'm going to say since X is in C1, right? It's actually in both of these. Since X is in C1, this means C1 is actually a subset of U. We already said C1 is a subset of U or V, but not both. And one of its points, X, is in U, right? That actually means that all of C1 has to be in U. It can't be in V because X is in U and X is part of C1. And so since, we know that all the points from C1 are either in U and V, but we know this one is in U, which means that all the other ones have to be in U because it's either one or the other, but not both, all right? So since X is in C1, this means C1 is in U. But X is also in C2. It's in the intersection, right? And that I didn't mean for that to be read. X is in C2. So for the same reason, C2 is also in U. All right? Both C1 and C2 are inside of U. That is a contradiction with something or other, right? What it means is the picture actually looks like this. C1, C2, U is here, and V just doesn't have any stuff in it, right? That means that's what the picture actually looks like. And can someone say, why is that a contradiction with something or other? Actually, this is not allowed for something. What could we contradict with is basically this. I mean, this is our assumption that was intended to get the contradiction, is that there's a separation. Yeah?
V can't be empty.
Right. This is not allowed in a separation because you have to have some stuff in each part. You can't have none of it on one side. All right? So this is not allowed. All right, really, technically, what we've shown, since C1 and C2 are in U, that means that C1 intersect C2 intersect V is empty. And that means that V, that's not allowed for V being part of a separation of C1 and C2. All right, so that means, I'll just say this is illegal if V is part of a separation of C1 union C2. All right. This triple intersection is really because we are, again, talking about connectedness of a subset. So you should be thinking about separations of a subspace, which is why I'm talking about this triple intersection. All right. So anyway, that's it. This is the end of the proof that two connected sets, if they have some intersection, then the union of the two sets is connected. All right? There is no similar property for intersections. Intersections of connected sets can be very strange. There is a property for products. I think maybe we should just do that next time, if that's all right. Yes, that's all right. All right, I hope you all have a good break. Thank you for coming today.